Good day and welcome back for part 2 of our discussion on differentiating logarithmic functions. In our previous video, we introduced several new exciting formulas. We saw that the derivative of the natural log of x is 1 over x, and the antiderivative of 1 over x is the natural log of the absolute value of x plus c. And I say exciting new formulas as we have now filled in a major gap that we had in our Calculus 1 experience. In Calculus 1, we had this formula for undoing the power rule. And with this formula, we could antidifferentiate x raised to any power as long as that power was not minus 1. But now if that power happens to be minus 1, we can now antidifferentiate it. So we are in a very nice position in terms of integration. So for the following example, I suggest that you pause your video, give yourself maybe 3 or 4 minutes, and evaluate that integral using a substitution. Keep in mind, when you evaluate a definite integral using a substitution, you must change your limits of integration. Now that you've thought about this for a few minutes, note we're going to require a substitution. And we want to choose u to be the largest possible inside function. That's reasonable. So in this case, 8 minus 3t. This forces du to be minus 3 dt, so that minus 1/3 du is dt. So very quickly and efficiently, we can rewrite our integrand so that it only involves u. Minus 1/3 is a constant. We pull that out front, and we're left antidifferentiating 1 over u. Now, previously that might have been an issue, but that is no longer the case. But we do have to remember to change our limits of integration. And in our original integral, we see the lower limit of integration corresponds to t equals 1, and the upper limit corresponds to t equals 2. So using our substitution, u equals 8 minus 3t. When t is 1, u is 8 minus 3, which is 5. And that gives us our new lower limit of integration. Similarly, when t is 2, u is 8 minus 6, which is 2. And that gives us our upper limit of integration. And it's worth recalling, there's no problems having your lower limit of integration being larger. We can still use the fundamental theorem of calculus just like we typically would. But whenever I run into that scenario and I have a negative sign out front, I will typically switch around those limits of integration and allow it to incorporate the minus sign. So note, if we instead integrate from 2 to 5, that takes care of this minus sign. It's absorbed into the integral. And now this might look a bit more standard. So now applying the fundamental theorem of calculus. An antiderivative of 1 over u is the natural log of the absolute value of u. And even though we are going from 2 to 5 in terms of u and everything's positive, in this course, whenever we antidifferentiate 1 over u or 1 over x, we will make sure to include those absolute values. So we substitute in 5, put a minus sign, plug in 2. So this would be 1/3 the natural log of 5 minus the natural log of 2. So once those quantities are substituted in, you do not need the absolute values. But before they are substituted in, we make sure to include them. You could leave your solution in this form. It is 100% okay. Or you could take this one step further and write it as a single natural log using our previous properties. So let's go ahead and look at one more antiderivative involving our new formula. So up to this point, we have been unable to antidifferentiate tangent. But I'm going to claim now we are able to do so because of this new formula. And that should give you a good hint of how to proceed. And think back to differentiating. If I don't recall the formula for the derivative of tangent of x, how would I go about differentiating tangent x? You would have to write it in terms of sines and cosines. So that gives us a very natural starting point for the antiderivative. Let's rewrite tangent as sine over cosine. And now that it's written in terms of sines and cosines, I would like you to pause the video and finish evaluating. And hopefully the observation you made is the only advanced method of integration we currently have is a substitution. And if we choose u to be an inside function, we would have to go with cosine. It's in the denominator. So if u is cosine, du is minus sine dx. So our sine dx is minus du. So we go from all x to all u, and we pull the minus sign out for convenience. And note, now with this substitution, it's a very reasonable antiderivative. The antiderivative of 1 over u is natural log absolute value of u plus c. And our last step is to resubstitute. Replace u with cosine, which gives us minus the natural log of the absolute value of cosine x plus c. And this is a perfectly acceptable way to write the antiderivative. But for fun, let's just go ahead and note that the typical formula you might see in the textbook is going to look slightly differently. It's going to be the natural log of the absolute value of secant of x plus c. And just to make sure we're all on the same page, why is that the case? Well, remember, one of our properties of the natural log is a constant out front can be made an exponent inside. Cosine x raised to the minus 1 power is 1 over cosine, which is secant. But just to reiterate, leaving it at that previous step is certainly okay with me. So let's go ahead and move on to one more example dealing with differentiation. So we'll finish this video up by differentiating a logarithm other than the natural log. So in this case, log base 5 of x e to the x. And in order to do so, I'm going to make just an observation to the side, linking back to something we mentioned at the end of our previous section. When we introduced properties of the logarithms, we had this change of base formula. We said log base a of x can be expressed as the natural log of x over the natural log of a. Where recall, this natural log of a that we have in the denominator is a constant. And we could very easily write this as 1 over the natural log of a times the natural log of x. This allows us to very quickly and efficiently get a new formula of differentiation. If I want to differentiate log base a of x, we would differentiate 1 over the natural log of a times the natural log of x. And because 1 over natural log of a is a constant, we can pull it in front of the derivative. And the derivative of the natural log of x is a formula that we are aware of. It's 1 over x. And this gives us a new differentiation formula to work with. The derivative of log base a of x is equal to 1 over the natural log of a times 1 over x. And if you've been following my recommendation of keeping a one-page overview of important formulas and properties, we certainly now have a couple new formulas in this section that we can add to it. So let's apply it to this specific example. The derivative of log base 5 x e to the x. So in order to differentiate, we will need the chain rule, right? We have an outside function, log base 5, an inside function, x e to the x. So using our new formula, the derivative of log base 5 of x is 1 over natural log of 5 times 1 over x. So we've differentiated the outside function. We now substitute in the inside function and multiply by its derivative. So we've combined together our new formula of differentiation with the old and familiar chain rule. Now, to finish it up, we have one derivative we need to evaluate still. And we can differentiate x e to the x using the product rule. So we think derivative of the first times the second plus the first times the derivative of the second. And recall the derivative of e to the x is e to the x. And if I want to take this a step further just for fun, in the top we have e to the x times 1 plus x. And in the bottom we have natural log of 5 times x e to the x. So we could also, cancel off the e to the x, which is common to both the top and the bottom. Now note, even though we've evaluated this in one way, it's interesting to note that it's not the only approach we could take. So for example, instead of directly differentiating with the chain rule, we could rewrite this function using the change of base formula from above. This is equal to natural log of x e to the x over the natural log of 5. 1 over the natural log of 5 is a constant. We can pull that in front of the derivative, just like we did above. Now, though, we can use properties of natural logs to rewrite. We can rewrite this as the natural log of x plus the natural log of e to the x. And remind me, what is the natural log of e to the x equal to? Simply x. So when we differentiate from left to right, we would have 1 over x plus 1. And I will let you do the simplification, but note this formula is identical to the formula that we have above. And it's always worth kind of reiterating or mentioning that there's very rarely one right way to do something. It's more often about finding the way that works for you. And that finishes our current discussion, but let me just remind you that you should be spending a significant amount of time working suggested and practice problems. And as you're doing so, if you have questions, do not hesitate to reach out. In our next video, we will continue on this discussion by specifically exploring our old formula for differentiating an exponential function and improving upon it. So stay tuned and take care.